And why are you doing this testing? Because do you think the industry needs additional testing? Do you think it
I
needs this
think I
clarity?
think it I think it's kind of crying out for a need for testing because nobody. I mean, I know you guys do your own testing, and people like Bob Dennis does testing, but most companies don't. I mean, Steve does his own testing, but I find very few companies are showing any kind of testing report, any kind of, any just way to show that what they're saying is what they have.
Mm,
And on top of that, they're not promoting the right parameters in any way, in my opinion. But
hmm
do we even know the intensities that they're listing are actually the intensities? I mean, we're just taking their word for it.
Yeah, and that
So,
comes to my next question, really. When we say testing, people might be thinking we're testing the fabric, or what is it you're actually testing, and what do we need to be more? What needs more clarity in this market?
well, really, it's just testing the whole. If you imagine a PMF full body mat, there's like a big cloud of energy, electromagnetic energy, across that mat. So we
Mm,
want to get a picture of that energy, like what is this? And for me, it's not just the intensity, but that's one of the things that we test is what's the intensity at 0, 1, 2, 3, 4, 5. So we can kind of see like a gradient of energy, right? And then we
mm,
want to test what I think is more important, the slew rate, because the slew rate or the Faraday induction is what's transferring energy wirelessly to from the mat to the body. It's not the intensity. And a good example of this is the wireless charging plates that you put your phone on, right? So you can charge your phone wirelessly. And guess what's charging your phone? It's the slew rate of the coils inside the Apple Mag charger or whatever wireless charger you're using, right? So
mhm.
it's not intensity. You could have a 10,000 Gauss magnet and it's not going to charge your phone. You can have, it doesn't matter how much intensity you have to change that intensity to transfer the energy.
Mhm.
So this is just physics. This is not even debatable. Intensity has nothing to do with transferring energy to your body. So slew rate is really the main thing that we're trying to test. So like, because again, it's how energy is transferred wirelessly.
Mm. I
So
think
I
that's a
mean,
good point because people that are using those wireless chargers, like I don't particularly use them with my phone, but people that are using multiple different versions, you have them in your car, you have them on your desk,
yeah,
and that sort of thing,
yeah,
and they charge the phone at a different intensity rate, at different speeds.
yeah.
And it's a good analogy. I've never thought about that actually. And it's, that's because of, some of them are more expensive and they're going to be designed a bit better, have a faster slew rate, maybe
Sure.
stronger. And they're, you know,
Yeah.
as we're trying to achieve here, they're charging the battery a lot quicker.
Exactly. And it's when you so I tell people like when you plug your phone in, that's like microcurrent therapy. You're directly adding current to the phone. Where the wireless charging plates are inductive coupling or like using Faraday's law of induction, which is what slew rate encapsulates, right?
Hmm.
So that's how energy is transferred. This is again not debatable. You need to either use magnetic or you can use resonance. We'll talk about resonance is another way to transfer energy wirelessly. But slew rate, as we'll see, kind of covers it all because when you have a high slew rate, you'll get a broad spectrum of frequencies. And we'll get into that a little bit later.
Hmm.
But as far as the testing goes, we're trying to test the intensity at different elevations, the slew rate at different elevations. We're testing the spectrum analysis through spectrum analysis. We're testing the spectral content. So, like, what are the range of frequencies in a PMF signal? And this is something that is reported in some PMF studies. And that so again, frequent we'll get into that a little later, but and with the help of a robotic arm and a very kind of a labor of love with David and spending all this money to get all these mats, we were able to get these accurate 3D pictures. We call them magnetic X-rays. And you can see some pictures at bryantmeyers.com/testing. And you can see kind of, and these images are not graphical illustrations by an illustrator. These are actual from measurements using MIT software to integrate all the numbers into a really a good picture of what the magnetic field kind of looks like over the top of a mat. And I mean, it's not going to be perfect, but it's the most accurate that I've ever seen. And I don't see
Mm.
anybody else has ever done anything like that. You know,
No, and I've seen some of the images that you guys have produced, and it's a really good visual interpretation because we talk about these crystal gem mats, and they have like four of those little rods
Yeah.
inside them at the top end of the mat. But
Yeah.
to the untrained person, they don't really know what that means or what that looks like. So when you see these tiny little magnetic fields coming out of the mat and reaching just maybe a couple of centimeters from it, and that's it.
Yeah.
It really helps to visualize that. So I hope that's something that you guys can do with a whole multitude of PMF mats, including Celerate. You told me you're going to do some proper intrusive testing on Celerate, which is great. The industry needs all of this.
Yeah, and the crystal mats, it's when you do the slew rate mat, because we have the maps of both the intensity and the slew rate. And some of the crystal mats, the intensity looks, I mean, it's not great, but it's like little tiny dumbbells of energy over their coils. But then when you look at the slew rate, it's just almost non-existent because they have a 8.3 millisecond rise time because they're just
Mm,
using 60 hertz, right? So
mhm,
the slew rate is dismal and it only covers a little tiny area. So this is why we also, or I kind of dissected these mats and measured the coils, and using a CAD software program made very meticulous, accurate, kind of images of the coil layout. So that way you
mm,
can see the total coil area, because what we found was that the energy from the measurements is mostly right on top of the coil and in the middle of the coil. You don't get much in between the coils. I mean, you get some, but the magnetic field lines diverge outside of a coil and they reinforce in the middle. So you don't get a whole lot of energy in between the coils. I mean, again, compared to what you're getting inside the coils. And
mhm,
especially right on top. Usually the hot spots on a mat are going to be the right on top of the coil. So
mhm,
so we took the middle measurements like by hand, but then this kind of robotic arm took 7,500 measurements at 1, 3, and 5 inches, and then MIT software extrapolates and interpolates that and makes like a. So that's why I said it's a good approximation. It's not perfect, but
mhm,
this software is pretty. I mean, AI, type of interpolation, extrapolation is pretty good. So
mhm.
it can kind of, it's like you're taking 3 points and it can kind of map out where the rest of the points are going to be, even though it might not be exact. It's still very close. And
Yeah,
again, it's
yeah, no, sure.
7,500 measurements. So this is a lot of data points, right?
Mhm,
To give like, it's like every inch is getting measured across the map
mhm.
at these three
And
elevations. Right.
And how does this translate in terms of people looking for systems? Because I always tell people to if they're talking to another manufacturer to ask them for if it's been tested and that sort of thing. But there's a particular line which I absolutely hate on websites, and it says third party tested.
Yeah.
For me, that's third party tested could mean anything.
Yeah.
They could be testing the fabric on top of the mat for
Yeah.
for
Well, for,
VOCs or something completely
yeah.
something
Yeah. Yeah.
completely different. For you, what should people be looking for? And if a manufacturer doesn't give the slew rate or anything like that, what does that tell you about that manufacturer?
Well, I mean, a lot of manufacturers I don't even know if they know what slew rate is, or I mean, maybe the manufacturers do, but the companies that that sell the product a lot of times don't. So they're just usually promoting intensity and frequency is kind of what, and then they get into all these gimmicks where, oh, we have these special frequencies for all these different things, and our waveform is special and patented, and nobody else has our waveform. We call our system PEMA or PEMI instead of PEMF because it's so better than everybody else that we had to come up with a different name. It's just all marketing. It's just there's no legs to stand on. I mean, and
Mhm,
then some of the company, I won't name names, but some of the companies say, "Oh, we have all this research," but there are a lot of white papers done by scientists that either developed the product or worked for the company. I wish I
mhm.
could name it. I mean, but so they claim that, oh, we're the only one that has all this. But you actually, and I did go through some of these companies that kind of just lean on what they call as research. And it's a lot of papers by, I'll just say I won't say the product, but Dr. Fisher, for example. He's got all these studies, but he developed the product. So it's like, well, and it's not like they're published studies in like a reputable journal. I mean, there's a
Mm,
few in there, but some of them with one company actually showed negative results that they
mhm,
never want to share that study. But as far as like, the parameters that they're promoting, it's just like you say, third party testing. Let's see that third party test. I'd like to see it. I mean, can you send me it? Can you send it to me? That's what I'd ask.
Mm,
And what are you testing?
yeah.
Because if energy is only transferred by slew rate and magnetic resonance, then you really should know what the slew rate is and the spectral content of the signal is.
Hmm.
Intensity, again, you could have the strongest magnet in the world that's not going to charge your phone. So the intensity is for measuring static magnets. Like Gauss, I tell people Gauss and Tesla, those are measurement units for static magnets, not PMF. PMFs are dynamic changing magnetic fields, and you need things like, repetition rate, Tesla per second, which is slew rate, spectral content, which is the bandwidth. These are the things that categorize or that will tell you what a PMF, or best sort of describe a PMF signal. And the wave
Hmm.
shape, let's see like an oscilloscope, you know, um, picture of the waveform, because I've looked at a bunch of square waves now, and now again, you're never going to see a square wave. You know what your
Mm,
signal looks like because you've seen it, right? It's a
hmm.
rounded off kind of triangle wave. Now, in the current, it is an actual square wave, but because of
Yeah.
the induction, it's the induction in the coils that rounds it out. So nobody's got a square wave.
Mm.
So that's another
I was I
misnomer.
was
It's like,
interested actually when
yeah,
when our
yeah,
engineers, when I first saw our wave,
yeah.
I was like, oh no, that's not ours. It's ours is a square wave, and they said, no, 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 that's what
That's
physically
what it is.
looks like. Is
No,
actually more like a sawtooth. In fact, it's
the system I recommend, it looks like that. We measured Steve Burdett's Nextian. His looks
mm,
like that. Robert Dennis's ISIS, which is a small coil, has a 160 Tesla per second slew rate. His looks the same way. I mean,
mm,
it just comes from when you look at the electric field and the voltage, it's a square wave in the current. But when you put that into the coils and when you measure the field, because of the induction in the coils and the resistance, it takes, it's like it's e to the minus whatever RC whatever over T or something like that. So that it you can't get a straight up. It's impossible.
mhm,
And the larger the coil and the more coils you have in series, the greater your inductance. So it's always going to round it out. Now, I did notice, like, measuring like our local the spectra I work with and your cellar rate local applicator, it is straighter. So it instead of so when you have like less inductance, instead of rounded, it's still like a triangle. It looks like a triangle, but it goes a straighter line because it's kind of
mhm,
getting up there quicker, where, when you have more inductance, it's slower to reach its peak. But still, the key thing is when you take the slope of that, and again, some are rounded out like this, and some are rounded out more like this. So the slew rate is the energy is from the bottom to the top, or you can take the slope towards the bottom, like, oh, you were seeing like on your lower intensities, you were getting a higher slew rate because the slope is higher towards the bottom. So if you kind of cut it off, you're going to have a steeper slope at the bottom,
mhm,
and then but anyway, you can take like the average slew rate from the bottom to the top, and that's really giving you a good indication of how much induced voltage is created, which is also the
mhm,
area comes into play there. Um,
yeah.
in fact, I've
And
realized that yeah, go ahead. I'm sorry.
I was going to say, I'll if anybody's watching this podcast, what I'll do is I'll get Josh to put on the Celerate square wave as to what we put into the device versus what you get physically out of the device. So
Yeah.
just as a visual representation,
And I'm
it's a
I'm
bit
gonna
like
send you
saying,
yeah, I'm
mhm,
gonna send you through email an image where it shows you how a square wave becomes this rounded signal, and it's just basic, what happens. And I got 4 examples: the Celerate, Nextn, R unit, the Spectra, and ISIS, which is all the same type of pulse generated square waves that look
mm,
like square waves on the current, but they all end up doing the same thing. In fact,
yeah,
the I1 signal, which is used in it's called the CRES, which is cartilage repair and electromagnetic stimulation, like group. It's a huge group of studies. They've done all these studies on cartilage repair. They're actually the 15 Gauss that Dr. Pollock talks about comes from their group of studies, and their signal, their I1 is the same. It looks the same type of thing. So they're
mhm,
using so whenever you have a pulse generator capacitor discharge, that's kind of what you see. Where the function generator square waves look a little different. They're kind of a
mhm,
little wonky at times. It's like, what's that? It's like this
mm,
little thing. But anyway, I'll send you
Yeah.
some examples of that because just don't.
Hmm.
Yeah, your signal is fine. That's just what happens when you put it in
Yeah,
the
yeah.
field.
And that's it. Just to dumb this right down, it's a bit like saying a car is stopped and then it's 60 miles an hour, then it's stopped, then it's 60 miles an hour. If you need to take into consideration the acceleration in between, and if you imagine that as a diagram, that's
Yeah,
kind of what you'll get. But anyway, we've got really lost in slew rate really quickly because we're both really passionate about it. So
move on. Yeah, let's move on. Yeah.